Good morning, welcome to new lecture. Today I will talk about torsion of shafts with rectangular cross sections and torsion of shafts with thin walled cross sections. See what is the difference, and if we have a shaft with rectangular cross section, what we should do, what is the difference. Previously we looked at the shaft with circular cross section. Circular cross section for shaft, if we apply torque, the behavior is totally different. With the shaft, the cross-sectional area is rectangular or square shape. Of course, square is kind of rectangular. And of course, there are similarities, but a lot of difference too. Let's look at first the torsion of shaft with rectangular cross sections. So, rectangular cross sections, something like this. Long side, we will assume the length is A. Short side, we will assume it is B. Let's look at the shear stress distribution here. Of course, I will not explain how we will end up with the formula, because that is a little bit advanced topic and you will not see in undergraduate level. Of course, later on in advanced topic, in advanced mechanics of material lectures, I will prove that. We will have that formula and I will explain precisely how we came up with this formula. But for now, I will give you formula and I will explain what is the difference with circular shaft. One of the similarity and difference I'm writing here. So here again, if we have rectangular shaft, successive cross sections rotate relative to each other about the shaft axis. We had this exactly for the shaft the shaft with circular cross section too. Here, shear stresses and strains means shear strains again are produced. So again we will have shear stresses and shear strains. But this is big difference, the third one. Cross sections do not stay flat. If you remember, for the shaft with circular cross section, after we apply torque, cross sections, those cross sections, they were perpendicular to the shaft. They remained again flat and plane and perpendicular to the shaft. Here, cross sections do not stay flat. Pay attention, do not stay flat. They warp or deform out of plane. Another difference here, shear. Stress in general does not act perpendicularly to lines emanating radially from the shaft center. So here the behavior is different from what we had before. So the solution of this you will find in Theory of Elasticity or Advanced Mechanics of Material books. Here, in order to find shear stress, if we apply torque in the centroid of the cross section, tau will be T C1 A B squared. T is torque, we are applying external torque, and internal torque will be equal, of course, if one end, for example, fixed. A is the long side of the rectangular, B is the short side of the rectangular, C1 is coefficient. I will tell you what are those coefficients. It depends on the ratio of A over B. Twist angle phi here, it will be TL C2 G A BQ. So twist angle will be T torque times L, the length of the shaft. C2, again another coefficient, it will depend on the A over B ratio. G is shear modulus, A long side of the rectangular, B is short side, to the power of 3 or Q. So if we compare with what we had before, if you remember, what was the tau? Tau was T R over J, and what was the phi? Phi previously was T L over G J. These are for shaft with solid or hollow cross section, but the shape is circular shape. Here is rectangular shape. You see the difference. Now let's look at the coefficient of C1 and C2. C1 and C2 will depend on the A over B ratio. For different ratio, there are different numbers. I write those for only 3 numbers. A over B is equal to 1. It means square shape. A over B is equal to the 2, and A over B greater than 10, or practically we assume it goes to infinity. Here is C1, C2. If we have a square shape, it means A over B is equal to 1. C1 is 0.208, C2 is 0.141. For ratio to 0.246, C2 is 0.229. If A over B is greater than 10, it is 15, 20, 40 or something, roughly it is equal to 0.333, both of them 0.333, and this means is equal to 1 over 3, 1 over 3. So if the ratio of A over B is big enough, greater than 10, with good approximation, roughly we can assume C1 and C2, both they are equal to 1 over 3. This is for torsion of shafts with rectangular cross sections. And now here it is clear because we define the torsional stiffness T over phi. From here, if we find T over phi, it will be equal to G A B cube over 3L if A over B, is greater than 10. This will be torsional stiffness, and you remember previously it was J over L. See what is the difference for shaft with rectangular cross section. If the ratio of A over B is greater than 10, it will be GAB cube over 3L. Let's look at the torsion of shafts with thin-walled cross sections. What does that mean? Thin-walled cross-section can have any type of shape. For example, something like this. Or again, circular shape, something like this. Or square shape, something like this. But it is closed section and thin-walled. Thin-walled, it means this thickness. If we compare with radius, thickness is very small than that radius, cross-section radius or cross-section length. So thickness, for example, it is 2 millimeter, and assume this thickness, it is 2 millimeter, and this is, for example, 40 centimeter. We can assume this is thin-walled cross-section. If we apply torque to thin-walled cross-section, what will be shear stress and how we can find torque angle or twist angle. Regardless the shape of cross-section, we can prove the formula. For example, I assume one thin-walled cross-section. Thickness thickness is very small, okay? And this is in the axial direction, L. If we apply torque here, this torque means we apply torque in this direction. What will happen? We will have shear stress, and shear stress, it will be similar to the shear flow, something like this. The section, pay attention, should be closed section. If it is open section, for example, if we have flat plate like this, and we roll it, and we make it like shaft with cross section, circular cross section, but it is not closed, so similar to this. Something like this. In that case, the behavior is totally different. If we apply torque here, this is similar to rectangular cross section. We bent it only, that cross section. So this is A, this is B here. This length will be A, the thickness T will be B. But if we weld it here, we make it closed, in that case we will have shaft with thin walled cross section similar to this, and shear stress distribution is like this. If we cut it in axial direction, if we cut one small element, for example, if I cut it like this, one small element, I cut it and I will take out, and I will look at to this small element behavior here. What we have, if we cut one small element, something like this, here we have, for example, if we apply torque like this, shear stress. This shear stress will produce another shear stress in longitudinal direction. Sorry, this direction is wrong. I should correct it. If this is in counterclockwise direction, and this is my positive, for example, X direction, top side will be in the positive direction, this will be in inverse direction. Here at the corners, okay, at the corner, if this one in this direction, this one should contract that, it should be in opposite direction, or this one in this direction, so this one will be in opposite direction. So look at the direction. I assume one small element, I cut it in the longitudinal direction. The length of this element, I assume it is delta x. Even I assume the thickness, for example, it is not uniform. Here the thickness of the wall, it is T2. Here the thickness of the wall, it is T1. And again, this is delta x. And longitudinal direction, I assume it is my x direction. If I write summation of forces in the x direction is equal to 0, in order to have that element in equilibrium, summation of forces in the axial direction should be equal to 0. If This shear stress, I assume it is tau 2 and this is tau 1. What will be the forces? Tau 2 T2 delta x, force in the positive direction, minus tau 1 T1 delta x. This is F2, this is F1, should be equal to 0. Summation of forces in horizontal direction is equal to 0. From here, tau 2 T2 delta x will be equal to tau 1 T1 delta x. Delta x from both sides, they will cancel each other. So tau 2 T2 should be equal to tau 1 T1. So always tau times t, it will be one constant value, and we will show with lowercase q, and we will call it shear flow. Shear flow. So shear stress times thickness, we will call it shear flow. Let's look at to now what is happening here in the cross section or axial section. Look at to this element. If this element, shear stress on this element, produce force like dF, that force times the distance perpendicular to line of action of this force. I show with, for example, lowercase p. dF times p will produce dt part of our torque. If I make summation of all these dF times p in entire cross section, that will be entire torque I am applying here. So T will be integration of dF times p. From here, see what we can write. From here I can write that is equal to, if I write this one more time here, T is equal to integration of dF times p. What is the dF? dF will be tau, stress, this is stress, times t, thickness, times ds, the length of this element in the curved direction, or the length of curve element. I show ds times p. This integration of this will give us entire torque T. Tau times T, it is shear flow. I show with Q, that is Q, times P ds. From math, we know P times ds, integration of P times ds, that will be equal to 2 times of area enclosed by mid-surface. So instead of that integration of P times ds, I can write, I will pull Q out of integration, integration of the P ds will give us 2 times of area enclosed by mid-surface. So I can write this is equal to 2q AM. AM stands for mid-surface, area enclosed by the mid-surface. So from here I can write Q, shear flow, is equal to T divided by 2AM. Because Q was equal to tau times T and Q is equal to torque divided by 2AM. If we put these equal, I can write tau shear stress is equal to T over 2 AM times T thickness. So finally, if I summarize everything, we had here if I have shaft with thin-walled cross-section, something like this, we apply torque T. Shear stress is equal to torque divided by 2 AM times lowercase t. This T is torque we apply. This T is average thickness. AM is the area enclosed by mid-surface. Which means this area. And 2 is coefficient. So for cylindrical shape shaft, if we apply torque T, the length is L, tau shear stress will be T divided by 2 AM times thickness. If this is inner radius and this is outer radius, RO, you can find, for example, if it is circular shape, AM will be equal to pi Rm squared. What is Rm? Rm will be inner radius plus outer radius divided by 2 average. So AM will represent area enclosed by mid-surface here. T is the thickness and lower and uppercase T is torque. We can find here shear stress. In similar way, because phi is equal to TL over GJ, and J for thin-walled cross-section, J we can prove in static, J for thin-walled cross-section is equal to 2 pi T thickness Rm cube. So instead of J, polar moment of inertia, if you find polar moment of inertia for cross-section, thin-walled cross-section, it is 2 pi T thickness Rm cube, and Rm is average radius. You can plug here and you can find twist angle. So if I summarize what we had today, for shaft with rectangular cross-sectional area, for shaft with rectangular cross-sectional area, tau is equal to T C1 A B squared. Phi is equal to T L C2 G A B cube. So for shaft with rectangular cross-sectional area, if we apply torque, shear stress is equal to torque divided by C1 AB squared, and phi twist angle is equal T times L divided by C2GAB cube. And A is the long side of the rectangular, B is short side, and L is the length perpendicular to the board here, or length of the shaft. If A over B is greater than 10, then we can assume roughly C1 is equal to C2, and that is equal to 1 over 3. If we have shaft with thin walled cross section and it is closed section, so torsion of shaft with thin walled cross section, torsion of shafts with thin walled cross sections, and that is closed section, something like this. If we apply torque T, in that case here, tau shear stress will be equal to T torque divided by 2 AM times T thickness, and phi will be equal to TL over GJ. For this kind of thin walled cross section, polar moment of inertia J, we can find it is equal to 2 pi T Rm cube, and Rm is average of outer and inner radius, and AM is the enclosed area by mid surface. So this is the difference. Here, this section, if it is not closed, if it is open, like this, it is not closed, if it is open, the behavior will be similar to the rectangular cross section. Length of this curve will be A and the thickness will be B. But if it is closed, in that case, we will have different behavior, and shear stress distribution will be like this. So I think it is enough for today. Thank you so much for watching this lecture, and see you next session. Bye bye.